So our final speaker is Elise Schriber. How are you?
Yeah.
Okay. And while they're getting set up, I'll introduce her. She's currently an associate staff scientist at LCLS, and she did her PhD at the University of Connecticut, working in the Holman lab and also working with Berkeley Lab's CCTBX team, developing the small molecule SFX method.
Thank you. Thank you so much for inviting me to speak today. So my name is Elise, as was mentioned. I'm an associate staff scientist, also an instrument scientist at LCLS. So my talk is also sort of a broad scale what we need and what we can help at LCLS do to assist data processing. So my method is small molecule SFX. So rather than doing protein crystallography, we look at small molecule structures. And one of the biggest problems when we use this method, especially in the high throughput way that we do, is we have an incredible need for speed. I was really excited to remember that video game from the 90s. So this, we kind of discovered this bottleneck accidentally. I was a terrible lab chemist. I hated it. And my boss wanted me to do chemistry. And I just was like, I can't, I'm just not good at this. So we realized we could make beautiful microcrystals using soluble thermal syntheses that were so easy that I could do it. But growing single crystals was not easy. And it turns out that across the board in the field of chemistry and material science, there is a big problem with growing large enough single crystals to do conventional X-ray diffraction. For instance, hematite anhydride, which is a analog for the malaria hemozoin pigment. 30 years research program, no structure that explains a lot of the properties that we're seeing. So we started with these hybrid materials, but it turns out it was a very broad scale problem across both fields of chemistry and material science. So this bottleneck was huge. And the way that we solved it is through a collaboration with Dr. Daniel Paley and Dr. Aaron Brewster and Nick Sauter and the whole CCTBX team at LBL. Where thank you everybody for already explaining how SFX works. So I can kind of just run this quickly, but very similar to the way protein SFX works. The difference, of course, being that we have to derive our unit cell dimensions directly from the XFEL data because these are totally new materials. Oftentimes there is no unit cell. There's no real knowledge about what the material is. It's a true unknown. And also our unit cell has to be super accurate to use the indexing method that was developed by Dr. Aaron Brewster. So we get our unit cell dimensions directly from the XFEL data, which is the first step that differentiates us from protein SFX. And it's also a very time-consuming human intervention necessary process. And if we have any errors or problems, it can actually toast the whole indexing convergence, really slow down our ability to get structures. So we solved some of these problems. We were able to do our merging. We got our first structure in 2020. And the publication of the method happened in 2022. It was a huge multi-institution collaboration, and it took 5 years to get there. But we realized that our group wasn't the only group to experience this. And through the method developed, this method, we've been able to solve 55 structures and counting since 2019. So we're really pushing the envelope in terms of high throughput materials discovery. It helped kind of open up the class of metal organic chalcogenolates. But we realized we can't hold this in and just, keep it to our group. And that's such a big problem in the field itself. We should expand it outwards. And like Martin talked about, I am an instrument scientist at LCLS, but I also am a big fan of not having users present. So we realized that developing a mail-in program was the easy way to do fast measurements at LCLS. Normally, of course, we do these kind of big, large-scale projects, kind of hero experiments, but there's a great use case for quick measurements that don't require users to be present. It opens up the LCLS and XFELs to more people who may not have the funding or ability to travel to LCLS or the experience level needed. And it also allows us to leverage the LCLS-II HE high rep rate to just do rapid measurements with very little instrument scientist intervention. So we started out our first kind of 2 pilot programs, and you can see that the number of samples and the number of user groups scaling rapidly with interest. So we already are running into a major data problem and bottleneck just now with the LCLS-I data. So the fastest solve we got for the first program was 15 minutes, which was fantastic, but you can see that our structure solution rate is very low, 8%. So we kind of rely so heavily on our data processing team to get us to that point, but I do believe that LCLS and us as a facility and as in instrument development and all of these things can also play an active role in making it easier to get structures. So this is more of like a, what can we do? What ideas do people here have to kind of improve the instruments themselves to make them better at assisting data processing? Because we can't all heavily rely on these experts all the time. We also need as a facility to develop internal methods to make it easier when we do these kinds of high throughput measurements. Our second experiment went a little bit better. We changed our sample delivery method. That was a big improvement, but we still had a 25% solve rate. So we're still really low in terms of getting structures to users. And when you think about conventional crystallography and micro-ED, you can oftentimes get a structure within a couple of hours. So the time between data collection, the time between a structure solution is significantly larger at an XFEL. And we want to figure out how we can actually like speed up that process. So I kind of think of this like Star Trek, because XFELs kind of are like Star Trek. Right now we're kind of in this alpha beta phase, and we need to move towards like the next generation, so the enterprise generation. But this also means we scale up the data, we scale up the amount of data we're collecting, and we really need to figure out better ways for data reduction. So can we dump blank images or useless images when like directly on the detector, as opposed to like, pushing them over to S3DF or to NERSC? Can we kind of use our large area detectors more efficiently? We also have problems where, because we're oftentimes measuring these like kind of inorganic lattices with very strongly diffracting Bragg peaks, we can damage the detector sometimes. So how can we do detector avoidance leveraging computational tools? That's something that's an active project that we're trying to figure out. But in LCLS-II HE, we're going to be able to get these complete data sets so quickly, but how do we get to the structure solution components? Where can we develop better tools, these digital twins, to assist us and kind of think about where we might have errors that kind of propagate through the data sets. So I want to be able to leverage all of the computational tools to kind of drive the efficiency forward for this. And of course, moving away just from the high throughput measurements, we can also consider things like pump probe for small molecules and other kind of more excited state studies, because most material science and chemistry happens in the ultra-fast time scale, so it really utilizes LCLS quite well. And then, of course, I have my ultimate aspirational goal for the LCLS-X era, which is like 10 years plus down the line. Right now, we are the only XFEL in the world that offers a mail-in program, and maybe that will change. I hope it does. But a global service can really only happen if we're able to get structures to users quite quickly, or else they will turn to other methods that are faster. Even though in the material science and chemistry communities, it's not quite as competitive, you can still get scooped if you're waiting 3 months to get a structure. So my goal is to have a specialized end station just for small molecule SFX, where we can really design an instrument, a data processing pipeline internally, at least, to be able to really like get these information out quickly. And that involves kind of specialized tools, thinking about how we design our detectors better, to better suit these kinds of experiments where we are not doing single photon counting. We're mainly looking at these very brightly diffracting Bragg peaks that oftentimes damage the detector. So the other aspect of this is that we can also move towards these excited state projects as well if we have an end station that's especially designed for this technique. And I think the data processing aspect is kind of one of our biggest bottlenecks right now. And although we have an amazing team developing really cool brand new tools, I think that as a facility, we also want to be able to support them as best as possible to make sure that all of our internal tools are also providing them with all the information and metadata they need, and also the information we need to make rapid decisions, which for mail-in programs especially, we need to be able to screen samples quickly and know when a sample's a lost cause, essentially. And then, of course, as we get these larger area detectors, we also run into a problem with being able to process like these very huge arrays and very large number of arrays in the LCLS-II HE era. So there's a lot of exciting things that we can do with small molecule SFX, but there's also a lot of challenges and kind of future needs that we'll have to solve pretty quickly in the next couple of years. And so I'm asking you guys as a group to help us and kind of help us figure out how we can push, how we as LCLS can help make this method more efficient and more and better. And that's it.